In exercise 3D, we look at another application of motion. Now, this particular one is called simple harmonic motion. It's not going to be a concept that's foreign to you. Maybe its name you've not heard of before, but the actual concept, I'm sure you've all played with a spring and you've compressed the spring and you've watched it, you've let it go and you've watched it bounce up and down. Basically, if we get a good understanding in terms now of what we've studied in motion and called displacement, velocity and acceleration, if we can get a good understanding of displacement, velocity and acceleration for, say, as you can see in your notes here, say that red ball on the bottom of the spring and what it's actually doing, then you will be able to master this application of motion as it's referred to as simple harmonic. So, you'll need to be familiar with the terms, and most of these terms you've come across before. You've come across the concept of a period, you've come across the concept of amplitude, and obviously time. The only one really that we haven't spoken about before is this concept of equilibrium. So all equilibrium is the position that the spring sits in when there is no force on it. So if we don't compress the spring or if we don't extend the spring, the position it sits at under no force is equilibrium. Which sort of makes sense in that it is equal, the force from above, the force from below is equal, it has equal distance to its maximum displacement, etc. Now, what we really also need to be able to understand is like I said before, the displacement, the velocity and the acceleration, because these are just functions in terms of time. And you can probably see here, if this is the graph of the displacement, then you see that the displacement is actually following the path of a nice sine curve. And so our trig will become important again in this application. I'll just touch on this official definition for simple harmonic motion, only very briefly because we'll come back to this in another exercise later on. It says simple harmonic motion is any motion where the acceleration is proportional to the displacement. Now, at this stage, we don't really want anything where acceleration is in terms of displacement. We want acceleration to be in terms of time and velocity to be in terms of time. And so when we're faced with this situation that we know the acceleration is proportional to displacement, we've got a totally different situation. But we know the calculus that can help us cope from there. And just keep in mind that we'll look at that a little bit later. Acceleration is proportional to displacement from equilibrium and is directed back to the equilibrium position. What it's really saying is that the force, if there's a force that is always pulling a particle back to this state of equilibrium, then it's called simple harmonic motion. So a particle on the end of a string is not the only example. You can see here that it says that if you were to observe particles about a sound wave, then you would see the particles moving as the sound wave goes past. The particles move in a similar manner. It's probably not something that most of us are familiar with, but this one I think is the rise and fall of the water according to the tide. And you'll often get a question about tides, so just be aware that if it's a question about involving the tide, then it will be referring to simple harmonic motion. And because the particles follow this nice wave pattern, then we'll expect that the functions are trig functions. So moving on to look at, for example, displacement, which is not unusual that that's where we start, the displacement time equation for simple harmonic motion. I'm just going to jump straight to mathematically what they are. Now, Mr. Ma has done a really good explanation about simple harmonic motion. He has a physics background, and he has been able to put together a really nice presentation. I've put the link to his presentation on our OneNote, and you might prefer to stop at this stage and listen to that. It does go for almost 12-13 minutes, I understand. If you are wanting the background to why this equation for displacement is this sine curve, function, or the cos function, then you will get that and a whole lot more if you watch that video. So, like I said, you could stop this video now, watch that one, and maybe come back and listen to the rest of this, or I'll quickly go through this and the rest of my notes and not go into too much detail, because you can get a much better, clearer explanation with Mr. Ma's video. Okay, so if we look at this function for displacement and think about our trig curves and how we've studied them, we know, and keep in mind that a number out the front, a number in here in front of the t, which is our variable, like our x, and alpha are constants, and a and n must always be positive. But because they are constants, I guess, well, a can't be 0, and nor can n, but alpha could be 0, a could be 1, n could be 1. Then it would be really simple. It would be just the function x equals sine t. That's as simple as it could actually be. Now, we know what those graphs look like. We know what putting a number out the front does to the sine curve. If I put a 2 outside of sine x, or sine t now in this case, then it made the sine graph have an amplitude of 2. And the same thing's going to happen, except we're going to actually name it amplitude. And it's actually going to have some meaning in terms of the displacement of the spring. So, of course, yes, if our amplitude was 2, then the actual particle has moved 2 units above equilibrium, and that number actually appears in the equation as the number at the front. Other graphical features of our trig curves also apply. N here impacts on our graph by either increasing or reducing the period. We squash the graph up or we stretch the graph out. So a period is normally 2 pi. However, we've seen the impact of putting a number in that spot. And alpha slides the graph, doesn't it? We've looked at the translation not only of trig graphs, but of all of our graphs, where we've put a number in this position, and we've seen the impact that a positive number pushes the graph back, and a negative number in this position pushes the graph forward. So just keep in mind that a, n, and alpha are just numbers. And likewise here with this format for displacement. You can probably guess that mathematically we would call in between maximum and minimum amplitude, that we might call it the origin, so that's the equilibrium position, and that does just make it easy for us to form graphs and call this point. But you know, in reality, if I hold a spring there and have a particle on the end of the spring, equilibrium could be anywhere. There's no defined origin until we describe a situation. We've talked about the period t being 2 pi on n, and we know that from our study of trig functions. And there's a much better explanation about phase in Mr. Mung's video, and that covers the next point as well. So here just a bit more talk about amplitude, but nothing that I don't think I've already touched on. It just says that in its most basic form, x equals sine t and displacement is cos t, that the amplitude would be 1, and that's not realistic, so hence we need to introduce an a. So I've just drawn the graphs there of y x equals a sine t, and you can see that if the particle starts at equilibrium, then it makes sense to start your graph there. Whereas if the particle was starting at its maximum amplitude, then it might be more convenient to refer to its displacement as a cos graph. And we've talked about the period, and we know that introducing an n in front of the t in this case will impact on the period, and the period will become 2 pi on n. So your sine curve stays exactly the same in this nice periodic shape. However, it's going to repeat itself in 2 pi on n times, and like I said, that depends on whether n is a number bigger than 1 or smaller than 1 as to actually whether the graph becomes compressed or stretched. The concept of a phase is just that stating that the particle doesn't start at equilibrium or either maximum or minimum amplitude. So we need to introduce now the alpha. Now you've seen the introduction of alpha into functions before. Probably didn't call it alpha, but you know that it results in a translation, a slight sliding right or left of the curve. So here's an example of the sine curve, but it has to slide back pi on 2. So it normally, remember the sine curve normally comes up here like this and then back down, and what's happened is a slide back of pi on 2. So it actually looks like that. This example is showing the impact of the change in period and the translation. We can take a little bit of time to look at those. And then finally, when equilibrium is not at what we want to call x is equal to 0. And you might wonder why you wouldn't, but you'll see some examples later where you can't adjust. There is a most convenient place to set displacement equal to 0, but then actually realise that equilibrium in that particular example won't be at x is equal to 0. Now, mathematically and graphically, we know that that just means now introduction of a number in this position, which is either going to push our graph up or down. I'm going to stop this video now and talk about the rest of the notes in another video.